Today we will start discussing the so-called quantum dynamics. When I say dynamics, obviously there must be time evolution, as was the case in classical physics as well. We have seen that there are equations of motions of Newton type or Lagrange type or Hamilton type, whatever. They all are essentially addressing the same question. If you have a state describing a physical system, in the classical case it's a set of coordinates and the momenta, then your main concern is what will be the state at a future time when the system evolves under the influence of an external agent. In classical Newtonian version, it's a set of forces, right? And in the other versions, more modern versions like Lagrange or Hamilton, it is the potentials really. So they are closer in spirit to the quantum theory. So we call it external agent, whichever way you define it, as forces or potentials. So it is one of the primary concerns of the physics, knowing an initial state and predicting a future state. The definition of state, of course, changes from classical to quantum, but that doesn't matter much. So all your concern is to find what that state is. There, finding the position and momenta. Here, finding the psi of t. Remember, we have defined the quantum state by an abstract vector in a linear vector space. For the continuum case, it's an infinite dimensional vector space, so it's a Hilbert space. But when we really ask this important question of dynamics or the time evolution of the states under the influence of an external agent, there's an important issue which is to be addressed, at least briefly. It is the very nature of time. Well, in classical physics, at least in the Newton's version of time, is an absolute parameter independent of the space. It's a constant flow, really. Well, Einstein, of course, unified it with the space, therefore it changed its nature, but still, well, they are both, space and time are parameters. When we move into the quantum mechanics, in the context of what we are doing, that is the non-relativistic quantum mechanics, time is still a parameter. Well, that's really a bit disturbing. You see, the way I am approaching it is embodied with hesitancies. Why do I say so? So the subject is quantum dynamics. Let's put this title as such. And of course, the important issue is the time evolution of the system, right? Time evolution of the system, whatever is it. The important issue is what is time. Time is going to be taken still a parameter. Okay. Now let me qualify this statement a little bit. This is not really that much mathematics or physics. There's a bit of philosophy involved in this discussion. I guess that these kind of issues have been taken up at the time of those great days of development of quantum theory by Schrödinger and by Born and others. Well, the sort of uncomfortable feeling about time is the following, particularly in the context of special theory of relativity of Einstein. Because time and x, in the context of special relativity, are thought to be forming the entities of a more generalized 4-vector. Also, there's a similar association of formally unrelated looking entities like the energy and the momentum. Again, in the context of special theory of relativity, they are still classical, of course. They are combined as the entries of a more general four-dimensional four-vector. Well, of course, to match the dimensions, you have to repair them a little bit. Put a C in here, a C in here to bring them to the same physical dimension. But that doesn't mean anything, right? C is a universal constant in the context of special relativity. So you're not changing anything. Time and space and energy and momentum are put together. That's nice. But when you move to the quorum theory, this is yet classical. Now let's move to quantum. So let's see what happens. When I move to quantum, then this U over C and P is, without any problem, put in the as the components of a four-dimensional operator whose zeroth dimension is the energy divided by C, and the space part is the P. And what do I mean, really? If it is, I'm saying that in agreement with the principle of correspondence, this is I h bar d by dct, that's U over C, the zeroth component, and this is h bar minus I h bar del. That is what it is. You may say, yes, we have identified the energy or the Hamiltonian operator with this and the momentum operator with this, but we were not really that concerned in this class that they were really forming the components of a four-dimensional vector. That is one of the pleasant surprises of the physics. Seemingly unrelated, two different fields, right? Special theory of relativity and quantum theory. And this particular correspondence of the energy and momentum vis-a-vis these operators is consistent with the fact that they are really forming the components of a four-dimensional four-vector. Strange, but I don't want to really make too much about it. This, as if there is some hidden, well, information in the quantum theory vis-a-vis the special theory of relativity. Although we are not doing relativistic quantum mechanics yet, right? This is the correspondence, which is nothing but this. A coincidence, let's say, really. We don't want to make, we don't want to push it too much. It must be just a mere coincidence, let's say. Anyway, there is nothing uncomfortable about that part. It is really well understood and consistent and all that. All the problem is in here. When we move into the quorum theory, we don't really put them in the form of a four operator. This is a four operator, but there is no four operator here. There is a time and there is an X operator like this. I'm not combining them. This is the non-relativistic quantum mechanics. So it is still to be taken as a parameter, a C number parameter. Although there have been several attempts really since the advent of the quantum mechanics in the late 20s and early 30s to construct a quantum mechanical time operator. And there were some physical suggestions why one should be looking for those, particularly in the context of a beautiful principle called the uncertainty principle. This is sort of, it's not a formal sort of raison d'etre. It's not forcing us to do so, but we know that between these operators, this is P operator and this E operator, there is some sort of uncertainty between these space parts of these two collections. And if one really forces that to the other sort of corresponding quantities, time and energy, and then it's tempting to think that there must be some kind of uncertainty between these two quantities as well. Energy is an operator in the context of quantum mechanics, which we call Hamiltonian. But So the present, in the present understanding, t is a parameter, but what if we elevate it to the status of an operator so that we could nicely introduce a rigorous way of introducing Heisenberg uncertainty relationship? Till now, that hasn't been really consistently materialized, unfortunately, or fortunately, I don't know. As I said, this is not really physics or mathematics, that's a bit of philosophy that we are discussing. But you may be wondering about another thing. Well, this is non-relativistic quantum mechanics. Of course, you go from here to relativistic quantum mechanics, that's a trivial generalization, and the ultimate theory is relativistic quantum field theory. That's really the how do you say, the present maximum state of understanding that we have vis-a-vis the nature, right? This is the standard model and beyond, etc. It's all based on the relativistic quantum field theory. You may be wondering, in that sort of three-step jump from classical physics to non-relativistic quantum mechanics and then relativistic quantum mechanics, of course, which was a big advent, for example, which opened the way towards introducing the untyped particle, which wasn't there till then. And the ultimate one is the so-called second quantization or quantum field theory, the relativistic form of it. You may say, is that problem resolved? Is there a time operator? No, what has been done in here is really funny in a sense. In this context, the position operator is demoted to the status of a C number together with the time. So they are just labels. T and X are C number labels, in, of course, continuum labels, right, of the fields. So instead of achieving a victory in the sense of turning time into an operator, what is achieved, what is done, managed instead is that to demote the position to the level of a C number label, so we are happy. So, but paradox is, well, seeming paradox, it's not a paradox perhaps, is resolved in a very strange manner. So we can really comfortably proceed towards understanding this time evolution problem in the context of non-relativistic quantum mechanics. That's the place we are working, right? Non-relativistic quantum mechanics. That's the subject of our class. Well, when we are discussing time evolution, remember, the title is quantum dynamics, so obviously systems should change under the influence of external agents, and we are going to follow how it changes. There are several approaches followed by certain authors. We are following Mr. Sakurai, therefore I will follow his footsteps. You remember one thing, how was the momentum operator? Well, X is a default operator, sort of. Although X is not the most profound operator that we can think of. I discussed that in detail several times in the previous hours. Well, that's sort of a default operator because it defines a reference frame, and you have to locate yourself to define your geographical position, right, when you are talking about a physical phenomenon. So because of that, thanks to Mr. Descartes, and it's there. But its partner, its classical conjugate partner, which is momentum, is introduced via the symmetry principles, right? It's introduced via the symmetry principle, which is the translation symmetry. Perhaps I have to put it up. Translation symmetry. And momentum is introduced as the generator of the translation in space. As I said, this is a very beautiful, really aesthetically beautiful way of approaching the problem, approaching or constructing quantum theory, because the we know that one of the most profound principles in physics is that when there are symmetries, there must be associated conservation laws. That's the Noether theorem. And physics, there's covariance under time translation associated with the energy conservation. There is covariance under space translation, so there is momentum conservation. There is symmetry under rotations, that's the angular momentum conservation. They are all related to the structure. Again, there's some philosophy in it of structure of the space. Space is homogeneous. So whichever way you orientate your axis and move here or stay in here and let time passes and carry out the experiment tomorrow, that's time translation, right? You don't change position. You carry out a set of experiments in here on this desk today, and then we come back and repeat the same experiment tomorrow. If we are really under the same physical conditions and boundary conditions, if we are producing the same results, it means that physical system is invariant under time translation. Time passes, but you repeat repeatability of the physical results. It is homogeneous in time and homogeneous in space in all ways. So we have the energy, momentum, and angular momentum conservations. Beautiful. I hope if you don't learn anything from this class, please learn these. These are the most profound principles that you can carry over to the future research of yours if you are going to go into the depth of physics. So this was one nice thing, and what we have done is that if there is a finite translation in space by an amount A, it was shown to be constructed by this. Remember, I use capital letters for denoting the operators, and small letters associated with them are the eigenvalues and eigenvectors. So this is the momentum operator. This is the finite amount of translation. So what we do is, here is the position x, and here is the position x plus a finite amount, and you moved from here to there, well, in a certain reference frame, for instance, right? Here. Then it is carried out, achieved by this operator. And the very definition, remember, it's so important that I cannot hesitate but repeat it. Then it acts on the position eigenvector, and it moves it to this finite position. Well, this represents a group, an abelian group really, because the generators, it turned out, we worked it out, that the generators of it, which are P over H bar, right? If you want to define a generator of translation, it is P over H bar. It was, again, this identification was made on the basis of physics and correspondence principle. We carry over many things from the classical realm to the quantum realm. And because we worked out the commutation relations of this G with the X, and we realized that it is the same as the XP commutation relation, which is again carried over from the classical physics via correspondence principle. If we identify this as the G, the generator, as P over H bar. That was nice. Now we will repeat a similar reasoning in constructing the time evolution. And we'll try to identify the generator of the time evolution, because it's time translation. As I said, here and tomorrow here, it's a time translation, right? You let time passes, you don't move in space. In four-dimensional language, there is a nice world line representation. I cannot hesitate, I cannot resist the temptation of showing it. If this is the light cone, the future light cone and past light cone, and this is the time axis, and this is a nice two-dimensional projection of the four-dimensional space-time, just for the record of it, x and one-dimensional x and t. And if you really follow the system sitting on there, You put your experimental gadget and repeat the experiment tomorrow. This is the world line, right? It moves along the t direction, and there's a point, say, at the origin today, and tomorrow I have to, I'm located on this particular position on this world line, if I'm not moving in space. Well, anyway, forget it. That's relativity. You'll see it more perhaps in the relativistic quantum mechanics or other classes. So it's the covariance under time translation will lead us today to the construction of time evolution operators similarly to this space translation business. So we will repeat same reasoning. We'll repeat same reasoning, similar reasoning, not same, of course, similar reasoning in constructing. Why I'm trying to qualify this? Because there are other approaches. For example, in other approaches that you may see in different books, one of the axioms of the quantum theory, after they introduced that state vector and the Hermitian operators associated with the dynamical variables, they further assume, propose as a postulate, that that state vector satisfies the following equation, which is the Schrödinger equation. If we had the Schrödinger equation as one of the basic postulates of the formal quantum theory, then life could have been a little easier. I could have used it more directly instead of going through this painstaking arguments. But this painstaking argument is beautiful because it's based on this symmetry, right? Time translation, symmetry, and the associated conservation laws. So we don't know the Schrödinger equation. So we assume we don't know it, and eventually when we find the time, construct the time translation, it will, as a byproduct, will produce the Schrödinger equation, which will, of course, be identified as the default equation of the quantum mechanics. Okay. Now, let me start formulating a problem. Well, there will be a slight difference with the book's notation. I respect this gentleman a lot, but sometimes I don't like his notation. It's a little cumbersome. Okay. So what I will say is that the problem is posed in the following manner. Now, suppose our system at a given time t0, most often than not, we'll take the t0 as 0. We start the chronometer and call it the 0 time, right? Well, but it is not, in order to keep the discussion as general as possible, for a while, I will use the notation t0, then eventually I will say that an ideal choice of t0 is 0. But for the time being, suppose we have a physical state like this at time t0, and we would like to follow its behavior under the influence of external agents, and we would like to find its future state. Okay, in order to pay respect to the author, I will drop it eventually as well. I will put a semicolon t0 saying that. It's not really a common notation, and just out of respect to Mr. Sakurai, I am doing it. Sort of this state evolved from this initial one. The presence of the semicolon t0 is reminding you that it's not just an arbitrary state t, it has evolved from that. Okay, that's just a notation. Okay. Well, we take the t to be later than t0, right? We don't want to go back in the lower light cone. We respect causality, so evolution is always in the future directions. So this t is later than t0. We don't want to move backward in time. So if this is really the question, if the initial state is known through a set of measurements, or whatever, you know what that is, and you know your external agents, and let the system evolve, and then you would like to know what that evolved state is. We write it formally in the form of following. Formal solution to the problem is via the introduction of an operator u in the following manner. Psi t semicolon t0 is u. I introduced a u. If you want, you can put the definitions. Doesn't matter. T0, psi of T0. That's the time evolution operator. Well, it's clear that in the context of quantum dynamics, our principal job is to find this u, right? If you know u, and if you know the initial state, you take that, you act on the initial state, and find your future solution. That's the way to make predictions. Well, of course, predictions are not deterministic predictions as in the classical case, but that's beyond the point. All different paradigms have different way of predictions, and this is the way you predict the future state. And once you have the future state predicted in terms of the initial one, you can answer all kinds of questions about that system, probabilistically again. Causality is okay. Time evolution follows causal principles, but predictions are probabilistic, not deterministic. Okay. But anyway, our principal issue is to find this u. Remember, when we were discussing translation, as I said, I will repeat, really, mimic the discussion in the case of translation. So I will follow the same steps. First of all, we have to work out the mathematical properties of the u based on the physical properties. Physics will dictate us certain set of mathematical properties, then I will use those mathematical properties to solve and determine the u. Notice one thing, that's bilocal. Please don't get upset about bilocality. This bilocality is no problem because it involves two times. There's an initial time and final time. It's only natural that it should involve two variables. That's the bilocality I'm referring to. Okay. Properties of u. The first property follows from the fact that we don't want to lose norm along the way. Time evolution should preserve norm. Let's write that physical principle, and let's see what follows, what mathematics follows from that. First, time evolution should preserve norm. That is, if, well, mathematically, it reads as follows. Whatever the initial norm is, remember, in the formal development of the quantum theory, we define the norm of the state, norm squared. You take the square and you take the square root, you get the norm of this Hilbert space vector. It should be the same as before. I want to express it in this manner. This is a more general statement than saying that if it is one before, it should be the same, it should be one later. Well, its value should stay the same. If it is one, it is one. If it is one half, it's one half. Of course, that doesn't mean anything in quantum theory because we know that norms should be one. What does it mean? Let me elaborate, remind you, refresh your memory a little bit, because you may say norm being one is really the probability conservation that we are more familiar. Well, this is really probability conservation, and let me demonstrate. Should preserve norm, conserve probability. probability. Okay, let me be careful about my vocabulary. It's half a minute reminder. We have seen it several times, but let's do it again. What is the norm? For example, what is that norm? Well, if you expand this in terms of the basis, let's take it to be one-dimensional for the heck of it. Just, you know, dx, x, and psi of t, right? You inserted an identity, completeness identity of the position operator's eigenvector basis. And this is you define to be your wave function, which are the coordinates in the position eigenvector basis. Then you introduce similar thing, dx prime, x prime, x prime. Okay, psi of t, x prime and x prime. Okay, we have to pay attention, right, to the order. So that's the identity we introduced. So this is the psi prime, psi star of x prime and t coordinates. And then you have x prime and x. So dx prime, psi star of x prime t, psi of xt, x prime and x. Use the Dirac delta normalization of the position eigenvector basis. Carry out one of the integrations. You get dx psi of xt squared. You say, of course, this you recognize, right? Well, quantum mechanical things is such that the sum over all options should add up to 1. If this is the probability density of finding a particle in a unit volume at time t at around x, then the sum of all these probabilities, according to the probability theory axiom, should add up to 1. This really adds up to 1. And in this notation, beautiful, very concise notation of Hilbert space, that's norm. Vectors are normed. So their coefficients in any basis, mod squared, summed over all options add up to 1. That's probability conservation. Fine. That was a refresher. So if this is so, of course, we say if it is normalized to be 1 at the beginning, it should stay 1. But its value should be preserved. Norm should be preserved, okay? You may say it's equivalent. Yes, it's equivalent, but I'm putting emphasis on this norm preservation. And that preserved value is 1. Could be any value, huh? So if I now substitute the definition that I have introduced for the u in here, u on psi t0, u dagger on psi t0 bra. So the right-hand side there is psi t0, u dagger, u psi t0, right? I write this as u times psi t0 here, and I write this bra as bra acted upon from right by the u dagger. That's really our conventions that we have developed before. This equals that automatically gives you, take the difference and write it. If you are pedantic, you can write it as such. 1 minus u dagger u psi t0 is equal to 0. These psi t0 are arbitrarily chosen. So this should be 0, otherwise you cannot get 0 at that level. So unitarity is proven. Time evolution should preserve norm gives you the first mathematical condition. U dagger u is 1, unitary. That's very nice. Well, we had similar property before when we were discussing the space translation. So it's very nice that we again have obtained a unitary operator for the time evolution. Okay, I think that's good enough without further elaboration. Now the composition property is sort of self-explanatory. Composition property, I will just show it in here in the following manner. If you go in, well, you're interested in making a transition from a T0 to T1 and ultimately to T2. You can carry out a single transition here, or you can carry this out in 2 steps. There is nothing which forbids you from that, right? And these two should be equivalent. If this time is homogeneous, whether you do it in a single shot or in 2 steps or more steps shouldn't change the result. The final state should be related to the initial state in the same manner. Let me write it. So what is the psi of T2? I can have it from through the direct shot as such, or I can think of doing it in 2 steps as in the following manner. I can write it as U, T1 and T0. I reach to, no, sorry, T2 to T1. I have to do it that way. T2, T1, for instance. But I'm just considering that transition. Then I have to connect this one to the previous. Okay, T1 and T0, psi of T0. Therefore, combining them gives me T2, T1, T1, T0, psi of T0. Now compare the first and the last. You are going from psi T0 to psi T2. Similarly, we are going from psi T0 to psi T2. So whatever prefactor are in the first and last line, they should be equal to each other because the final and initial states are the same. So the composition then reads as U T2 T0 U T2 T1 times U T1 T0. That picture leads to this composition property. Well, in mathematicians' language, the product of any 2 transitions, if they are properly ordered, it gives you another of the same sets of evolution operators. The product of 2 evolution operators gives you another evolution operator. As I said, provided that they are properly ordered. It's not that random in here, okay? Right, so, well, of course, there is a no transition case. Perhaps I should, no transition, which would mean that if you start from T0 and stay at T0, that should be the identity. So the identity is defined in this set. You see, I'm sort of working out the group properties, right? Going one by one over the group axioms. Identity is defined, it exists. Well, the inverse also exists. If you can go from a T1 to T2 via T2, T1 in here, if you carry out this transition, and you can think of the following transition going through from, you can think of going through T2, T1 in this direction via inverse of this, right? Because then it will bring you back to the same position. So inverse is defined. If the transition in one direction is defined and there is another one which takes you back to the same time location, so inverse is defined, exists. So all these 4 axioms, the first 2 being more physical than the, of course, the last 2, should be sufficient for us to construct the U. We do it in the following manner now. Let's think of infinitesimal case first. An infinitesimal time evolution, time translation, infinitesimal time translation. Notation is, let me follow the book's notation, yes. Let's start from T0 and move to T0 plus dt. Here's a picture. T0 plus dt. This is, the length of that is infinitesimal. As the identity is defined and it corresponds to no transition case, then this U T0 plus dt from T0 should deviate from the identity by an infinitesimal amount, just that amount. Because if I turn off the dt, if I let dt goes to 0, the point shrinks to here, and it corresponds to no transition case. So the leading term must be an identity. There must be plus or minus. I'll define the notation. It must be proportional to dt linearly, so that if I let dt goes to 0, it should go to the identity, right? That's the definition. So convention is to put minus I and to put an omega operator, which is the unknown operator yet. And I will work out the property of this omega. Well, immediately follows from, first of all, I can choose it. There are two ways always in this case. I can choose it to be a Hermitian operator, then unitarity follows automatically, because this infinitesimal form should satisfy all the mathematical properties I have listed, in the sense that I am constructing the U based on those mathematical properties extracted from physics. Okay, it's unitary. If I require the unitarity, let me follow this line of reasoning. Use unitarity leads you that omega is, capital omega is a Hermitian operator. Or vice versa. So let me put this two-way. You may require from the beginning that all physically relevant operators we are dealing in the context of quantum theory are Hermitian, and this should be associated with some kind of observable. Therefore, I require it Hermitian. Then you can demonstrate immediately that it is unitary as required for norm preservation. So the first condition is more or less trivial. Second, you can immediately check the composition is satisfied by this form. You work out this, you substitute this for 2. Okay, let me write it and I will ask you to demonstrate it on your own. Composition is the following. You start from T0, you move to a T0 plus dt1. Again, well, let me write it cleanly because there is not enough room here. This is exaggerated, of course, right? dt2. This is dt1, this is dt2. Let's think of two infinitesimal steps. You move from T0 to T0 plus dt1, and then add another dt2, two infinitesimals. You can demonstrate that this single shot and this two consecutive infinitesimal shots, they indeed satisfy the composition law that I have listed up there. That this single shot thing is equal to the product of these two in the opposite order. Time and the locationing of the operator, positioning of the operator in the order is opposite, right? Time moves in the towards right, and the operators are to be put in the reverse order. The future one should be put to the leftmost. The earliest one should be put in the rightmost. You have to pay attention to this reverse ordering. Strange enough, perhaps we have to use Arabic alphabet so that we can write. If we start writing from right, there would be no problem. Huh? So I think it's a good point to stop. And then here is, based on unitarity, we constructed it, and we have, in words, I demonstrated that it satisfies the composition rule. I ask you to demonstrate it. Spend 2 minutes to do it on your own, okay? So that's a good point. So, yeah, sure.
In the fourth postulate, U inverse exists. Does it mean, is it physically exists?
Mathematically exists. It means if you can carry out a translation in one direction of, say, in the future direction of time, and in principle, mathematically, it should possible to go back to the original. So it's the going backward in time is not forbidden because it's a continuous parameter, right? Also, you know, it's an external absolute label, yet still in the theory of quantum.
When we assume that omega is unitary, does it mean...
Omega is Hermitian.
Hermitian. Does it mean omega is physically possible?
It will turn out to be. It will turn out to be the case. Momentum turned out to be the generator of the space translations. It's only natural, remember the introductory philosophical remarks that I have made, it's natural to expect that Hamiltonian or energy operator is the generator of time translations.
Does it mean it can U inverse possible to exist?
No. It doesn't have, well, this being the generator is being a Hermitian operator doesn't have anything to do with the inverse operator of the U to exist. It does. These two facts are not correlated.
From that equation, U equals to I minus R.
Yeah.
Identity minus R. And omega, if omega exists physically, U inverse is also, because U inverse is
it's more or less trivial. As I said, if you can go this way, there must be a way of going back to the same time location mathematically. Although you cannot send physical information back in the past future light cone, this is a purely mathematical property. Think of the following, perhaps. Psi of xt and psi star of xt. Coordinates. Let's take these coordinates, wave functions. These two individually do not have that profound a meaning, but together they have the meaning, right? Because they define us the probability density and they enable us to carry out the expectation values. Why do I write these? This and that satisfies different equations. This satisfies the time reversed equation. So time reversal is sort of, in the context of quantum mechanics, it's like taking the complex conjugation. So there's a time reversal invariance at the level of Schrödinger equation because psi mod squared is the physically relevant thing. If you take the psi mod squared, psi times psi star, let t goes to minus t. Psi of x minus t, psi star of x minus t, psi star of x minus t is psi of xt, psi of x minus t is psi star of xt, so psi mod square is time reversal invariant. So mathematically you can reverse the time at the level of equation of motion for single entities. That's a very profound subject. I don't want to get into it. It's a beautiful subject, but shouldn't be confused. Time translation is something, time reversal is another thing. Here I move in one way, translate, and back another way. It's not reversing the time at all. Huh? It's taking, instead of going from T1 to T2, I go from T2 to T1 back to the same position, mathematically.